So let's imagine that we have an infinitely large plane and that we spread mass. Well, it's a massive plane, and the density is uniform. So we have uniform density rho m, and we want to find the acceleration that an object would experience if it were placed at some height, I don't know, z star from the plane, directly above the plane, let's say. Right, so this is the gravitational version of the same problem we did for electric fields. So we want to use Gauss's law for the gravitational field, which is integral of the gravitational acceleration field over a closed surface is equal to minus 4 pi g mass enclosed. And so we need to pick a closed surface on which to do this calculation, just like we had to pick a closed surface on which to do the electric field, to do the calculation when we had the electric field here. It's the same idea, except the field will be pointing in a different direction. So maybe let's look at this plane from the perspective where it looks like that. And so we are at a distance z star. And so it's clear that the field is in the vertical, pointing in the vertical direction, given that the distribution of mass is on the plane and it's uniform. So we pick a surface here. Let's imagine that that surface is, it could be any shape really, but let's say it's a circle. So if we look at it from a slightly tilted angle, it's really, we're constructing a cylinder. Okay, so here we have the top surface, and we are at a distance z naught, so we'll be at a distance z naught below as well, because we want the field G to have the same strength. The field G is pointing straight down, right? Because the field is pointing toward, it's an attractive field, unlike the electric field. And so here we have field lines representing G that are pointing toward the plane, and they have the same strength because we've chosen the surface appropriately. On the sides, of course, we could imagine that we're closer to the plane, and so the field here, G, is larger, but it doesn't matter. That's a bad assumption, as we know from the electric field case. We can make longer arrows here, but so the field here is a little bit closer than it is here, and so we could imagine that it's larger, but it doesn't influence this calculation because it's on that surface, right? It's on this surface here. It's grazing that surface. It's not piercing through it, so it doesn't add to that calculation. So we have a little cylinder. We do this calculation. We get only contributions here and here, and so we have twice G times the area. Now, I'm actually making an assumption here. I've chosen the normal to the surface to be inward. 2G times, well, given that I made a circle, let's say that there's a radius r, so 2G pi r squared, and that's the left-hand side. No contribution again here, just like in the electric field case, and here we do minus 4 pi g, and we have to figure out the mass that's enclosed. The mass enclosed is in here, right? So that's a little circle as well. It's a little disk. So here it is. It's the cross section here. That's how much mass is there. It's just the density times that area. So we have the density rho m times the area, which is the same as this. It's pi r squared. So that's Gauss's law for the gravitational field. And so we get that G is equal to minus 2G pi rho m, and we'll turn that into a vector indicating, well, what am I doing here? Sorry. I want to put an n hat, because the acceleration field is normal. It's opposite of normal. Normal would be that way, and so it's pointing toward the surface.